pre-calc, this is 1.5. I'm going to call this day 2 because of the worksheet we did yesterday to kind of introduce this. But today we're going to talk about the parent functions and transformations. We're going to start it. And the biggest thing that you're going to take from today is what parents are and what their t-charts are going to be, or tables, to start them. So a parent function, guys, is the most simplistic way for a form of any equation or function. And it can be used to create all the other members of families of that particular type. So, quadratics have a parent. Absolute values have a parent. Cube root, cubic, square root. All of those different things have their own parent graph that they build from, start from. And so what we're going to do is we're just going to select some of them, talk about some of them, so we can apply some certain skills, these transformations. And the coolest thing about it is that just because we talk about only 5 or 6 of them, the same structure, the same idea can be applied to any parent function. Like, I noticed that we're not going to talk about exponential functions, but yet you can do this. Then there's a couple others that we're not dealing with. Okay, a whole bunch of them actually, that we're not dealing with, but yet we still can apply all the changes to. So, what we have here is that we're going to start with linear and polynomial parent functions, or just the linear ones first. And we have a constant function, and if you have a constant function, there's not too much that we'll probably talk about of just like y equals 2. Because y equals 2, if I change the x value, nothing happens. If I change anything else, I can't really do much. I can add something to that, the graph will go up. If I take away something from it, the graph will go down. But it's constant. There is no x values. It's just a y value. That's a constant. We're not going to really deal with that. But we will deal with the identity function, aka the basis of all other lines, for the most part, almost all other lines except for vertical. And y equals x. If I add 5 to it, well, then the whole graph moves up 5. Or I could actually move it to the left 5. We talked about that already too, because that's one of our things from yesterday. So if I'm given a line and I need to transform it, translate it, dilate it, reflect it, I will start off with making a table for y equals x. That table is going to have, because a line can be anything, it's a straight line, I'm going to use my Fab 5. I'll use -2, -1, 0, 1, and 2. And when I put them into the function, if f of x equals x, that means y equals x. So if I put -2 in, I get -2 out. If I put -1 in, I get -1, 0, 1, and 2. It's the exact same thing. Look at the parent graph there. Is -2, -2 on there? Is 0, 0 on there? 1, 1, 2, 2, 5, 5, 8, 8, 10, 10? Yeah, they're all on there. That table can represent its parent, or the parent. And from here, I'm going to be able to make any adjustment that I would like. So today, we're just going to be doing this for these. And then we'll apply 1 or 2 of them in a bit. So, I crammed these ones all together. We have a quadratic function, we have cubic function, we have square root function, reciprocal function. Each one of these is a different shape. Each one of these has a different parent, or is a different parent. Each one of these will have a different table to start with. You should recognize that if it's a quadratic, it has a line of symmetry, and that it's a U shape. We all know that about quadratics. They're U in their shape. So, if I want to see what that U shape is, I need to have points on both sides of that vertex. And to do that, oh look, the vertex is at 0, 0. So I'm going to use my Fab 5. -2, -1, 0, 1, and 2. But when I put them into my parent, -2 squared is 4. -1 squared, 0, 1, and 4. Now here's the cool thing. I can either remember the parent's table completely, as in -2, -1, 0, 1, 2 is 4, 1, 0, 1, 4, or recognize that if it's a quadratic, it's going to be around home, because almost all parents are at home, and therefore, if I use my Fab 5, I can create the y values just by putting it into x squared. I don't need to memorize everything. You just need to memorize that the parent is around 0, 0, so use your Fab 5. Look at the cubic function. Can I still use my Fab 5 there? Would the Fab 5 be a good candidate?
No.
Why not? Take a look at what a cubic is. Bless you. Do you notice that it's on both sides of 0? One side of 0 does one thing and another side does the other thing. So therefore, and they are going the opposite directions. So therefore, I want to keep track of where is it going up, where is it going down, where is it changing. And I think the Fab 5 can really highlight that for yourself. So what happens when you cube -2? It's -8. Cube -1. Cube 0 and 1 and 2. So there you go. And again, what we're going to do is we're going to start with this. We start with this and then we move to everything else. We will move it, we'll stretch it, we'll shrink it, we'll move it left, right, up, down. Square root function. Can I use my Fab 5 for that one?
Maybe? No.
Why can't I use my Fab 5?
Because you don't deal with negative numbers.
Can't do with negative numbers. Negative numbers are outside my domain. They don't exist over here, guys. So what's the smallest number that I can put into square root?
0.
Yeah, I could put 0, then put 1, 2, 3, 4, right? So what happens when I square root 0? 1? 1. Square root of 2?
2. Well, it's square root of
Square root of 2, which is 1.414.
3.
What about square root of 3? Well, that's 1.73. And then 4?
2.
2. Wait a minute. So we got some nice ones in there, and then these things here are just not so nice, are they? Does it really matter? Like, think back to your quadratic function or the cubic function. Could I have put 1/2 in there and squared it? Back up into quadratic. Can I square 1/2?
Yeah.
Can I square -1/2?
Yeah.
But how come I didn't put that in there? Maybe should I have put those in there?
Well,
Do I have to?
no.
No, because if I connect -1, 1 and -2, 4, I will essentially say I'm passing through all of the x values between there, right? So can I use that same thinking and say I want to avoid putting in not nice square roots? So essentially say, okay, erase that. Start off again saying 0, 1, they're nice. But then jump to 4, 9, because those are 2 and 3. Yes, you can put any numbers you want into a T-chart. If I'm taking square roots, I'm going to pick perfect squares. If I'm looking at a cubed root graph, I'm going to look for perfect cubes. I'm going to tailor my table to what my function is. I'm going to make this a lot easier for myself. Cool? And again, we will change this appropriately with our transformations. Now, reciprocal functions. Hopefully you guys got to those last year or the year before, and you guys realize that there are certain things about this graph that you can never be. And those red lines that I just put on there would be called the new. Would be called the asymptotes. So this graph has asymptotes. We have an asymptote at y equals 0 and x equals 0. I cannot be at those values. So I need to actually state those as my parent. All parent graphs of reciprocal functions of 1 over x has this to it. Y equals 0, x equals 0 for asymptotes. But since I have a vertical asymptote here at the 0, it means it cuts my graph into two parts. That means I'm going to actually make two t-charts, one for the left side of that vertical asymptote and one for the right side. So put in like -1 and -2, 1 and 2. Because I need to identify, am I going to be in the top right or the top bottom? Or right bottom. Left top, left bottom. Where is it located? Because like you can see, they're going towards those asymptotes. All reciprocal functions will approach the asymptotes. That's what the definition of asymptote is. So it goes towards them. So when I put 1 over -1, I get -1. When I put 1 over -2, I get -1/2. If I put 1 over 1, I get 1. 1 over 2, 1/2. And then I can just move those points. Two more. And one of them we're not really going to deal with. But we will deal with absolute value. The absolute value, guys, is technically just a piecewise function. We'll learn how to graph a piecewise function at the end of this lesson. But in general, absolute value functions are these. You handle them the exact same way you would handle a quadratic. And so the quadratic and the absolute values are both centered around the origin. You will use your Fab 5. But what does the absolute value do to a number? Makes it positive. So absolute value of -2? 1? -1, sorry? 0? 1? And 2? And so again, we're going to start with those. And from there, we'll change it according to whatever happens. The greatest integer parent, though, it is f of x equals like a double set of brackets on there. I like how they say it's the greatest integer function, but really it's defined as the greatest integer less than or equal to x. Look what happens. If I start at 0, I can be 0. But as soon as I start to go to like 0.25, 0.5, 0.75, the output is only 0. It's not until I hit 1 that I make the leap and jump to 1. So it's almost like I got to take all the decimals and just throw them away. So until I hit a solid whole number, I stay at the same level. They call this type of function a step function because it looks like a flight of stairs or steps. We're not going to necessarily deal with this one right now. I want to do the others, and we'll come back on this one and kind of say, what can we put in for like a parent to kind of identify what changes, what doesn't change. Because I think this one will have a little bit harder time setting up a table for. So we may have to accommodate for that. First transformation, that is up is translations. So transformations in general are the change in the appearance of the parent graph. It doesn't change what the actual function is. So a quadratic is still going to be a quadratic. We're just going to move it left, right, up, down, stretch it, shrink it vertically, horizontally, and so forth. So that's the cool thing. You can't change what it is, but you can change the appearance of it. You can put lipstick on a pig, I guess, and it's still a pig. I don't know if that helped him. So, translation. A translation, guys, is what they're going to call a rigid transformation. A rigid transformation that has an effect on shifting the graph, and there are two types. There's a vertical shift that moves the graph up and down, and there's a horizontal left-right shift. Each one of them has a different letter associated with it, and that might be a little small in here. And so let's deal with the vertical shift or translation first. So the vertical translation here says that my new function based off of f of x is just plus k. If I add something after a function has already been applied, the y values will just go up or down according to what k is. It says that if k is bigger than 0, it's a shift up. If k is less than 0, it's a shift down. I relate it to this. You guys just put a hard week of work in at work. They gave you your paycheck yesterday, so you come to school with your pocket full of money, this line full of money, and all of a sudden you get to class and, hey guys, here's $20 for everyone. Everybody's money just went up. It didn't say, oh, you worked more hours, here's more money. It's just at the end, everything was done, here's $20, now everything went up. That's this situation here. Everything's been done with f of x. But then all of a sudden, if I add 20, the graph will have to go up by a factor of 20. Now, if we get to the same situation, and I say, okay, now everybody has to omit $20, everybody's money, no matter where it was, whether it was $10, $20, $150 in their pocket, their money just went down by 20. So the graph actually will sink or fall, go down, translate 20 down. So a k value is the up and down value. It's at the end of a graph. And then we come over here to the horizontal translation. This one is inside of the function. This has a play on what's going on. You're adjusting something. You're adjusting potentially how many hours you worked in a way. So, here's the thing. It says that it's an h value. It's x minus h. And if it's h units to the right, if h is bigger than 0, so it goes this way, to the right. And if h is less than 0, it goes to the left. Okay, so positive h goes to the right, negative h goes to the left. But, wait a minute. Look at our function here. It's f of x minus h, but yet it went to the right. And when it was said f of x plus h, it went to the left. It's because the original formula always starts off as x minus h. And if h is positive, like positive 2, so if I say, hey, h is 2, that means it'd be f of x minus 2. That's a right to translation. Then, we also can have, if h is a negative 3, you would have f of x minus a negative 3. And if we have that, a negative negative makes a positive. Therefore, you get a situation that it actually is doing the opposite, guys, of what our actual f of x or h value looks like in the equation. It does the opposite. We're going to see this again. When it's with x, it does the opposite thing. Okay? So keep that in mind. So be ready for some examples of this. I'm going to start you guys off easy here. We're going to get rid of this one. That's gone. Okay. First one, okay, A. I want you to graph f of h of x is equal to x cubed minus 5. And I don't want you to make a table for that, necessarily. I don't want you to make a table all brand new and then put the numbers in. Because the thing is about these, and that can be done. Every single one of our graphs that we will eventually graph, you can make your own table, find the exact values that you want to put in, get the values out, and make a graph. But the reason we go back to the parent is because we know where the parent's at. We know that if I use the parent's information, I will have a complete picture of what it should be like. And then when I start to move it, I can adjust for that. But when I look at an equation and I don't know where the center is, it's really hard for me sometimes to get a full quadratic or an absolute value or a square root graph. I might only have parts of it. Heck, for a square root graph, you may not even be able to find it because the numbers you want to put in do not exist. So, my suggestion is go back to, says use the graph of f to the third power, aka the parent, to be able to graph x cubed minus 5. Well, guess what? I don't have a graph right now for the parent, so you guys got to make one. So I suggest you put parent y equals x cubed and make a t-chart. What do I use for the parent of an x cubed graph? Anything special, or can I use my Fab 5, Fantastic 4? What do you want to do? I'm going to use my Fab 5. -2, -1, 0, 1, and 2. The reason? I wanted to have both sides of that cubic graph. And, cool thing is, I don't necessarily need to remember what the y values are because I can just plug them right in. -2 cubed? -8, then -1, 0, 1, and 8. Now here's the cool thing. I could graph that and I would get the parent's graph. Everybody agree with this?
Yeah.
Oh, we had it on the screen already. But that's not what it's asking me to graph. It's asking me to graph x cubed minus 5. So, what am I doing to the graph of x cubed when I say x cubed minus 5? What kind of translation is that? Down 5. I'm going to move it down 5. So that when I get to my new t-chart, which is y equals x cubed minus 5, I am moving the graph down 5. Wait a minute. If I move my graph down 5, do I have to adjust or move the x values to do that? No. So they will stay the same. But if I do move the graph down 5, I am doing actually what to my y values? Subtract 5 from y. And when you subtract 5 from y, you start at -8, you will fall to -13. Start at -1, you end up at, start at 0, 1, and 3. Yeah, that's pretty cool. Okay, watch this. You don't have to graph both of them. It would not be negative 3, it's positive 3. Because 8 minus 5 is 3. So I'm going to graph the parent in red, because I made a red t-chart there. Negative 2, negative 8. I think it's about here. And then negative 1, negative 1. 0, 0. 1, 1. And I need to make this taller. 3, 4, 5, 6, 7, 8. No, I'd say someone took a quadratic and then ripped the side down, right? Okay, that is the parent.
One of the videos he said like it was kicked in the stomach.
So, what we need to do here is graph the other one. And the other one you said was just move down 5. So, 2, negative 2, negative 13, which should be at the very end here. It's 1, negative 6, 1, negative 0, negative 5, negative 4, and 2, 3. Now it's a little bit wonky, but do you notice that the graph, every point was just picked up and moved down 5. You will not have to graph both the red and the purple. You would just graph the purple because that's the one we want. I'm showing this so that you guys can actually see that the graph has been fell 5.
Is it okay if we graph the parent
It
one?
is perfectly fine to graph the parent one. But that's not, again, what we're going to be the one looking for. Eventually, we're going to be graphing something we call the child, which will have multiple steps to get there. So,
What's this one called? The purple one.
the purple one, this would actually be a child graph. But we'll get there. Now, the next one. I want you guys to try that one on your own for a second. The quantity x minus 3 cubed. Here we go. With this one, what's going to happen to my graph on this one? It's going to go to the right 3. Yeah. And so, still need my parent. The parent, still the same, right? Negative 8, negative 1, 0, 1, and 8. Now, this one we'll put in blue. We just said it was right 3. If I move right 3, does it affect my y's? Would I be moving this graph up and down? No. So guess what? All the y's stay the
Same. Just adding 3 to the x's.
Yeah. All I'm going to do is take my x's and add 3 to x. That's the plan. The plan from there to there. Take the x values in the parent t-chart and add 3 to them. So negative 2 plus 3, 1. Negative 1 plus 3, 3, 4, 5. So, watch this. I'm going to put this on the exact same graph. 1, negative 8. 2, negative 1.
2.
And look at that. The graph compared to the red one was just shifted to the right 3 places. Okay, the last thing I want to talk about today is what if we reflected. So we're going to talk about reflections. So this is a transformation, and this one produces a mirror image of a graph where there's reflected about a specific line. The lines that we're going to talk about are the x-axis and the y-axis. And so what you need to realize is that if I put a negative in front of f of x, so f of x again has already been done. I've already applied, I've already got something, and then I make a negative. All of the y values that were positive now all of a sudden become negative, and any negative y value now becomes positive. So therefore, it gets flipped about the x-axis. Anything that was up here is now below, anything below is now above. Think of this. A negative x squared graph opens down. You guys have done this already. The graph opens down instead of up, simply by putting a negative in front. And it changes if I, again, put a negative inside with x. This time it flips it about the x-axis because instead of being positive x direction, it goes into the negative x direction. So this one affects the inside right away. So I wanted to take f of 2, but now I'll have to take f of negative 2. It's going to change it. And it flips it about the y-axis. Again, I didn't put examples to this stuff because I think it's just easier once we get into our parent, family, child method to see those in action versus just piecewise. So today your homework is for day 2, page 52, 8 through 9. Have a great day.